So we will have the last talk of motives and whatnot. And it's my pleasure to introduce Akhil Mathew, who will tell us about K1 local TR.
Okay, so yeah, thank you very much for the invitation. So in this talk, I'd like to describe some sort of structural features of TR and its K1 localization. And these are going to somehow be parallels of classical results that go back to Thomason. So let me start by recalling some of them. So Thomason's results are in the context of K1 local K theory. So let me just check this is working. Okay. So K1 local K theory. So after Thomason. And so, right, so the idea is that when you consider the K1 local, so if you consider the algebraic K theory of a scheme, and then K1 localized, so this is going to be with respect to some prime number, which I'll now call L, but this has sort of somewhat nicer properties than algebraic K theory itself, and furthermore, in many situations, it's not so far off from algebraic K theory, so it's sort of a good approximation. So let me state sort of three general theorems about K1 local algebraic K theory. So consider consider K1 localization. So this is an operation on spectra, and it's going to be at an implicit prime L. And we're going to apply it to algebraic K theory, and we have the following results. So first, let me call this Theorem A, which states that K1 local K theory satisfies H descent on the category of QCQS schemes. So this is an H sheaf of spectra on QCQS schemes. So Theorem A is somehow it's a very general descent property of K1 local algebraic K theory, and as I've written it, it holds with essentially no finiteness hypotheses. We're just assuming that we're working with QCQS schemes. So recall, I guess by comparison, that K theory itself satisfies Misnevich descent in this generality. By the result of Thomason and Trabeau. So in the same generality of QCQS schemes. Let me also comment that, right, so this notion here, when I say that it's an H sheaf in this generality, what I'm referring to is the notion of a sheaf of spectra that is, I think, somewhat slightly weaker than the notion of a hypercomplete sheaf of spectra that was more classically considered. So let me say that LK1K so it's a sheaf of spectra in the sense that, well, I believe was first really explored by Lurie, and in particular, it's not a hypersheaf. So it's not a hypercomplete sheaf of spectra. In this generality, it's only a sheaf. And so an example of what this distinction means is that if when you're working with sheaves of spectra in this generality, it's not true that you can detect when a map is an equivalence by testing on stocks. So it's not true that a map of sheaves is an equivalence if it's an equivalence on stocks. And there's no analog of a local to global spectral sequence. But nonetheless, there is a sort of good theory of sheaves of spectra, and this result is true. Right. So Theorem A is proved by Thomason, or it's a sort of consequence of stronger results of Thomason under further finiteness hypotheses. And so I guess later in this lecture, I'll maybe briefly explain why Theorem A is true in this form as well. So let me just say that, let me charge this, sorry. So Theorem A is proved under stronger finiteness hypotheses by Thomason. Finite. Right. So now let me state the next theorem. So theorem B. And so now this is going to be under some of these finiteness hypotheses. So now let me suppose that I have a QCQS scheme. So let's say it's a QCQS scheme. And let me assume furthermore that it's a scheme over Z adjoin 1 over L. So it's a scheme over Z adjoin 1 over L. And it's a finite Crawl dimension. Now the main finiteness hypothesis that we need to assume is that we need to suppose that the virtual cohomological dimension of the residue fields with mod L coefficients is uniformly bounded. So suppose the virtual cohomological dimension with mod L coefficients of the residue fields K of X, as X ranges through the points of X, is uniformly bounded.
What is the virtual cohomological dimension?
So virtual cohomological dimension so the cohomological dimension is going to be the dimension for which, so you take this field K of X and you consider its Galois group. And the cohomological dimension is the maximal dimension in which you can have non-zero cohomology of that profinite group with respect to some discrete coefficients. And the virtual cohomological dimension means that we're allowed to, we look at the cohomological dimension of any finite index subgroup. So it's the same, in this case, it's the same as the cohomological dimension outside the prime 2. And in the case of the prime 2, you just have to add like a square, you just have to add a square root of -1, and then they become the same. Okay, so suppose the virtual, so thanks for the question. So suppose the virtual cohomological dimension is uniformly bounded. And then the conclusion is that you can get a very strong handle on what this K1 local K theory is. So there is a complete, exhaustive filtration on K1 local K theory. So let's call this fill greater than or equal to star of the K1 local K theory of X. And this is a filtration in it's a Z index filtration. So I'm requiring that it's complete and exhaustive. And there's an identification of the graded pieces. So GER I of the K1 local K theory of X is identified with, well, you take the L-adic cohomology of X, the ZL cohomology of X, k-twisted by I, and shift by 2I. So for I and it. And so in particular, from this, you obtain a spectral sequence starting from the L-adic cohomology of X and converging to the K1 local K theory of X. And it's going to be a very strongly convergent spectral sequence under these hypotheses. Okay. So theorem B is well, somehow it's a much stronger. So in particular, this under these finiteness hypotheses, it gives you H descent, but this is really sort of a hyperdescent or Postnikov descent statement. So this is follows from étale hyperdescent, which is what lets you construct this filtration. This filtration is the Postnikov filtration in the, I guess to be precise, I should say the pro-étale topology. So this follows from étale hyperdescent of K1 local K theory, which holds under these finiteness assumptions. Right, so I should say something about the attribution. So this is proved by Thomason. So this is proved by Thomason if you have a stronger assumption on the residue fields. Stronger requirements on the residue fields. And the reason is that Thomason has to use, so I guess when Thomason was considering or was proving these results, the Balance and Lichtenbaum conjecture was not proved. And Thomason used well, Thomason was using a piece of it, the Mercurius-Suslin theorem, and so needed to assume some stronger hypotheses. But in fact, these requirements on the residue fields can be relaxed to this finiteness of the uniform bound on the VCD. So in this form, it follows sort of basically via Thomason's methods from the Beilinson-Lichtenbaum conjecture. So it follows from the work of Voevodsky, as proved by Voevodsky. Oops, spelling. Sorry. Voevodsky and Rost. And this argument is explained by, it's worked out by Rosen, Schwan, and Osweier. So the fact that you can get the statement with exactly these hypotheses. Okay. And theorem C is a sort of Quillen-Lichtenbaum statement. So theorem C is the assertion with sort of similar finiteness hypotheses that that algebraic K theory is already sort of asymptotically, well, with L-adic coefficients, K1 local. So suppose, right, so theorem C is suppose X is as above, and suppose the virtual cohomological dimensions of the residue fields, the virtual cohomological dimensions at the prime L of the residue fields are all less than or equal to some number D. So then the conclusion is that the map from K of X mod L to its K1 localization of K of X mod L is an equivalence in high enough degrees. So it's truncated and the bound is given by the maximum of D minus 3 and minus 1. So this map is truncated with respect to that number. In other words, the homotopy fiber of this map lives in degrees at most this max of D minus 3 minus 1. So this is sort of a Quillen-Lichtenbaum statement that mod L algebraic K theory under these finiteness hypotheses is going to agree with its K1 localization in large degrees. So this is also a consequence of the Beilinson-Lichtenbaum conjecture, and is also done by Rosenschwan and Osweier. And again, but actually the methods that go into proving such a statement already go back to the paper of Thomason and Trabeau. Okay, so I guess if sort of combine these theorems, well, I mean, let me just make some comments. So if you imagine that, for example, even if you're working with, say, algebraic varieties over an algebraically closed field, so if X is a variety, then if you look at the mod L K groups, they're quite large. So if you look at K0 of X with Z mod L coefficients, so then this is going to be related to the tau groups on X, and in particular, it's something that could be very large. Could be an infinite abelian group, even if you're over an algebraically closed field, and it's not going to vary in families in a nice way if your variety varies in a family. So this is quite large because it's related to the Chow groups. But on the other hand, when you apply this process of K1 localization, you get something that's really ends up being purely topological. But K1 local algebraic K theory is somehow purely topological. So, for example, if you were working over the complex numbers, then you could recover it from the homotopy type of your algebraic variety. It would be the topological K theory of your algebraic variety. So it only depends on the homotopy type, and somehow it's a much coarser invariant. Okay. But somehow the higher algebraic K groups, when you get into large enough dimension, they already start to become these purely topological invariants. Okay, so so that's a little bit about K1 local K theory. Are there any questions at this point before I move on to TR?
What did you mean by the homotopy type of the variety?
Oh, sorry. I guess I mean. Well, so I guess you could say the étale homotopy, the L-adic étale homotopy type of the variety if you're over an algebraically closed field. which is not the complex numbers, or the literal topological homotopy type of the complex points. Yeah, thanks for the question. Okay, so yeah, so I guess a goal of this project was to somehow develop analogs of these sort of three results in the context of TR. And so maybe I want to start by maybe saying some things about what is TR and where it came from.
Akhil, may I ask you?
Yeah.
So there's a question in the chat.
Sorry.
You also get arc descent.
Right. So you probably won't. So you probably won't get descent for these types of infinitary topologies, like the V topology or arc topology. The H descent statement in theorem A is really sort of a finitary one. So maybe it's worth saying that when I say the word H sheaf here, I'm only sort of working with finitely presented maps. So maybe I should be careful about. So I think typically the H topology, maybe traditionally the H topology is considered for Noetherian schemes, but there's you can talk about the H topology for arbitrary QC/QS schemes, but then in this context I want to work with finitely presented morphisms everywhere instead of finite type. Right. So if you drop the finite type assumptions, probably this is not going to be true.
Okay. Before you go on, is there a way of removing the keyboard from your screen?
Oh, I'm sorry. Sorry. Thank you. Okay.
Okay. Thank you.
Sorry, I didn't notice that. Thank you. All right. Okay. So now let me talk about TR. So what I started the talk with was K1 local key theory, and in particular was sort of an L-adic phenomenon. So this was really focused on schemes where L is invertible, and we're seeing like the L-adic homology. So TR lives somehow in a different world. So TR is really something that you study when you're interested in p-adic invariants of p-adic rings or p-adic schemes. So TR is going to be some sort of p-adic theory rather than an L-adic theory for p-adic rings. So maybe a rough summary is that TR is an object which arises in the theory of trace methods. So TR is an object. So it's an object that you can define, say, for a ring. And it's an object which arises in the theory of trace methods in algebraic K theory. So in particular, it has been classically used to study the p-adic algebraic K theory of p-adically completed rings. So very roughly, TR is built. So maybe I probably won't have time to give a full definition, but roughly TR is built from THH or topological Hochschild homology. So this is topological Hochschild homology. From its structure, from the rather rich structure the topological Hochschild homology has as a cyclotomic spectrum. So from its structure as a cyclotomic spectrum. So so maybe sketch. Right, so a sketch is that the structure of a topological, of a cyclotomic spectrum means that when you form the topological Hochschild homology, so if R is a ring, one can consider the topological Hochschild homology, and this sort of cyclotomic apparatus lets you form various other objects which are called the CP to the n fixed points. So I should say that, right, so THH of R is a spectrum, and it's possible to define fixed points THH of R CP to the n. So there is it's possible to form fixed points. Well, it's possible to define spectra called the fixed points of the CP to the n action on THH of R. So it's possible. So can form let's just say it this way, can form a family of spectra written this way. And these spectra are related by a bunch of maps called the Frobenius, Verschiebung, and restriction maps. So this is for n greater than or equal to 0. And these are related by various maps. So, so there's the Frobenius map, the restriction map, and the Verschiebung map. So the Frobenius, so the Frobenius is going to go from the Cp to the n fixed points to the Cp to the n minus 1 fixed points. The restriction is also going to do the same thing. Let's write it this way. And the Verschiebung is going to go in the opposite way. So so these can be formulated in the language of equivariant stable homotopy theory. So the Frobenius is essentially sort of the inclusion of fixed points of a larger group and fixed points of a smaller group. The Verschiebung is a transfer. The restriction map is somehow the subtle point in the cyclotomic theory. But essentially, the way that you're supposed to think about this is that this is analogous to the structure that you see on the Witt vectors of a ring. So this is supposed to be analogous to the structure on the Witt vectors of a ring, because if you take the length n Witt vectors, well, you have some tower of length n Witt vectors, and they're related by Frobenius restriction and Verschiebung operators. In fact, there's a precise connection. So there's the following theorem. So this theorem is due to Hesse, Holt, and Madsen. So it states that if you consider this collection of spectra of fixed points of THH, and if you take pi 0, you exactly recover the Witt vectors with their analogous maps. So the theorem is that pi 0 of THH of R, Cp to the n fixed points, is isomorphic to the length n plus 1, well, p-typical Witt vectors of R, and all the above become Witt vector maps. So all of the above maps in the cyclotomic theory reduce to the maps that you see on the level of Witt vectors that you define purely algebraically. Okay, so so the definition then is that TR of a ring R is defined as the inverse limit of the Cp to the n fixed points. So it's the inverse limit of these Cp to the n fixed points along the restriction maps. Up here, there are two ways you could form the inverse limit, but we're going to take it over the restriction maps. So maybe I should say restriction to avoid confusion. Yeah, so this is called TR. So classically, classically, TR played sort of an important role. It played a really significant and major role in the approach to topological cyclic homology via equivariant stable homotopy theory. So TR plays a central role in the approach to topological cyclic homology. And the reason is, well, so if you take the Cp to the n fixed points, well, they had these, not only these R maps, but also these F and V maps. And in the inverse limit, TR is also equipped with F and V maps. So TR is also equipped with F and V maps. And TC of R, or topological cyclic homology. So this is, I guess this is, I should say, in the p-complete context or p-typical context, is given as the homotopy fiber of F minus 1 on TR of R. So it's a homotopy equalizer of the Frobenius and of the identity map on TR of R. Okay, sorry, yeah.
The R is any ring when you're talking about this? Or?
Yeah. So, but yeah, I'm working. Everything is going to be implicitly p completed. Yeah.
Okay.
Yeah. Thanks. Right. So yeah. So classically, in approaches to computing topological cyclic homology, somehow the strategy was to go through a computation of TR. And the way that you would go through a computation of TR is that you would start by computing THH, and then you would inductively compute these CP to the n fixed points, I guess using a tool called the, I guess called the norm cofiber sequence. Well, anyway, there's a way of sort of inductively computing the CP to the n fixed points of THH of R, and then you would form this inverse limit given by TR, and then you would form the Frobenius fixed points. Right. So yeah. So let me maybe mention some examples of this. Some calculations of TR. So there's the following theorem of Hesse-Holt. So the theorem is that if R is a so let R be a smooth algebra over a perfect field K of characteristic P. And so then the assertion is that when you form the TR of R, so when you form the TR groups of R, these groups are given by the de Rham-Witt groups. So TR on the level of homology is recovering the de Rham-Witt complex of R. So let me just say this is the classical de Rham-Witt complex of R in the sense Ulysses de Rham-Witt complex. And the operators F and V on TR recover the operators in de Rham-Witt theory. So you obtain a complete formula for TR for a smooth algebra in characteristic P, given by the de Rham-Witt complex. So this was also extended to mixed characteristic in work by Hesse-Holt and Madsen. So here the result is a little bit more complicated to state, but let me state it and explain what one can do with it. So so in mixed characteristic, let's say we're in the following setup. So let K be a p-adic field. And let me assume that it contains a primitive p-th root of unity, and p is greater than 2. So the result is that there's a similar type of structure. So so let R be a smooth OK algebra, where OK is the ring of integers. So then the result is that well, let me also say that let little k be the residue field. So then the result is that, well, it's not exactly going to describe TR of R, but it's going to describe well, it's going to describe it up to bounded error, and the bounded error comes from the special fiber. So so maybe, yeah, so let me say it this way. So they defined an object called, well, maybe I'll just say it. So what they prove is that if you take the mapping cone of the transfer map from TR of the special fiber, so TR of the special fiber is something that's given by the above result. It's a de Rham-Witt complex on the special fiber, and map that to TR of R. So if you take the cofiber of this transfer map, and then on homology, it recovers the, on homology with mod p coefficients. Sorry, so that notation, the way I wrote that is maybe not the best. What they call it is it's some sort of, you can think of it as some sort of log TR with mod p coefficients. And what they show is that this is given by the absolute, well, an object that in fact they define, the absolute de Rham-Witt complex of R with respect to the log structure on the special fiber. So this is an object that they in fact define. So, right, so maybe let me just say why this is sort of a really powerful result and really powerful computation, which is that this, this leads to a purely p-adic proof of the Beilinson-Lichtenbaum conjecture for local fields. So this leads to a p-adic proof, and so this is prior to Grabowski and Rost. This leads to a purely p-adic proof of the Beilinson-Lichtenbaum conjecture for OK. So this is due to Hesse-Holt and Madsen. And can more generally be extended to certain complete discretely valued fields where you allow the residue field to be imperfect. So let me also say extended by Dicer and Hesse-Holt. So somehow this is a very powerful computation. Right. So in the approach, so this is maybe two examples of computations in TR. So in the approach to topological cyclic homology by Nicholas and Schulze, TR is somehow de-emphasized. So in the Nicholas-Schulze approach to topological cyclic homology, so TR does not appear. So you can build TC without ever mentioning TR. But in fact, let me mention that it's possible to sort of connect the Nicholas-Schulze approach to topological cyclic homology and TR. And in fact, it's possible to formulate very precisely what is the structure, that TR carries. So this was done by Antio and Nicholas. So construction, which is due to Antio and Nicholas, is that you can very precisely identify the structure that TR carries. So can identify the structure on TR, and it's the following data. So first of all, there's an action of the circle group S1 on TR. So this is refining the circle action on topological Hochschild homology. And second is that you have a Verschiebung map, which goes from the CP homotopy orbits of TR back to TR. And this is going to be S1 equivariant. So you sort of upgrade the Verschiebung to a map from TR CP homotopy orbits to TR. And this is required to be S1 equivariant. And you have a Frobenius map from TR to TR CP homotopy fixed. So this is again S1 equivariant. And you have this is an extra data. You have a homotopy of the composition F composed with V, which goes from TR HCP to TR upper HCP, is the CP norm. So it's the norm map for the group action CP, and this is also required to be S1 equivariant. So throughout here, so as in the work of Nicholas-Schulze, you identify S1 with S1 mod CP. So maybe I will not try to spell it out precisely for lack of time. But so in their work, Antio and Nicholas call this structure a topological Cartier module. So this structure is called a topological Cartier module. And a key result that they prove, which actually is going to be used quite essentially in this project, is that the theory of topological Cartier modules is sort of a decompletion of the theory of cyclotomic spectra. And so they prove that cyclotomic spectra, so these are going to be p-typical bounded below cyclotomic spectra, are going to embed fully faithfully into topological Cartier modules. And the essential image is going to be those which satisfy some completeness hypothesis. So yeah, so maybe let me just say briefly that yeah, they developed the structure and it's going to play a role in what I will explain, because somehow it's important to know the structure that TR has, and it's actually very helpful to have this sort of decompleted notion of what a cyclotomic spectrum is. Okay, but so maybe I should state the main results now.
May I ask a question?
Yeah.
Briefly. So is TR universal in some sense with respect to this structure?
I don't think so. I mean, I think so TR is something that it's a localizing invariant of stable infinity categories, and it also has additional structure. And I think one could try to formulate a universal property of TR along the lines of say the universal properties of K theory. But I think
okay, so not
going to be able to. I think yeah. But yeah, I don't know. Okay, so yeah, so maybe let me formulate the main theorems. So, okay. So, right, so somehow they're going to be parallels of the three results for K1 local K theory. So yeah, so the first result is that, so K1 local TR satisfies H descent. So, right, so this is parallel to before. So in particular, K1 local TR satisfies étale descent, but étale descent in this setting is actually pretty easy relative to say what happens for K theory. But let me give an example of the type of statement that this implies. So an example of the type of statement that this would imply is the following. So let R to S be a finite map, finite and finitely presented, map of rings. And suppose I have a finite group G, which acts on S, such that, well, I'm not going to assume that the map from R to S is a G Galois cover, but what I'm going to assume is that it's a G Galois cover after I invert P. So after inverting P, this is G Galois. So an example would be if you have some extension of p-adic fields, then look at what happens on the ring of integers. So that's not going to be Galois if you have a ramified extension, but it's Galois after inverting P. And so then the statement is that, right, so if you take the K1 local TR of R, then this maps via an equivalence to the K1 local TR of S, where I take the G homotopy fixed points. So you get sort of a Galois descent in the generic fiber. Right, so I guess I should say this is a consequence of H descent and the fact that this construction annihilates objects which are purely P torsion. Okay. So let me scroll. So the next result is going to be an analog of well. Right, so maybe actually I'm going to state three results about TR and its K1 localization. I'm actually going to state them in a slightly different order. So the second result is going to be an analog of the Chromological.
Akhil, could you move up just a little bit?
Yeah, sorry.
To the. Thanks.
Yeah, sorry, maybe later.
Thank you.
Thanks. All right. So yeah, so theorem B, right? So I guess I'm going to state this slightly out of order. So right. So suppose R is a regular ring. Right, so sorry, so I'm going to state a result to the effect that TR is asymptotically K1 local. And this is going to actually assume a little bit more, it's necessarily going to assume a little bit more than for K theory. In particular, it's going to need regularity. So suppose that R is a regular P torsion free ring. Of Krull dimension D. And maybe for simplicity, let me suppose it's essentially a finite type over the ring of integers in a p-adic field. I think you can state something a little bit more generally in the paper, but let me state it like this for now. Right. So then the statement is that the map from the the map from TR of R with FP coefficients to the K1 localization of TR of R with FP coefficients is D minus 1 truncated. So TR is going to asymptotically agree with its K1 localization under sort of similar hypotheses as in K1 local K theory, but you do have to add this regularity assumption. It would not be true without regularity. So yeah, so that's sort of a Chromological type statement. And let me say that, well, first of all, I should say that this result, if R is actually smooth over OK, so I should say that this is a consequence of the work by Hesselholt and Madsen, which actually I just wrote above. This is a consequence of the work of Hesselholt and Madsen if R over OK is actually smooth. So if you have something which is smooth over a DVR, well, plus maybe P is greater than 2. Well, anyone can actually remove that in their work, but so this is due to Hesselholt and Madsen if you have something which is smooth over OK. But somehow maybe, well, in fact, what Hesselholt and Madsen prove is much stronger. They actually compute both sides. So they compute both sides in terms of the de Rham-Vid complex. So the result is much stronger. But on the other hand, I guess this result is proved in a completely different fashion. And it is applicable in this context of you just need to have a regular array. Yeah, so in proving it, you don't actually have to compute anything. Okay, but now let me maybe state the main result, which is the analog of Thomason's spectral sequence. And here I think I actually, well, as far as I know, I think right now I need to assume that I have something which is formally smooth. So suppose R is smooth over OK, where K is a p-adic field. So then the conclusion is that there is a filtration. So again, it's going to be a complete exhaustive filtration. On K1 local TR, such that the ith associated graded piece, so GER I, is given as the cohomology in the arc P topology over spec of R of the presheaf given by W of O, W of the structure presheaf, twisted by I, and then shifted by 2I. So if I have time, I will try to explain what the object on the right here means. But this is supposed to be an analog. This is supposed to be an analog in the setting of well, in the filtration on K1 local K theory. You saw the l-adic cohomology, the ZL cohomology, K twisted by I, and here you're seeing some other type of cohomology which I don't understand very well, but can be defined and hopefully can be computed as well. So it's an analog of Thomason's setup, analog of Thomason's spectral sequence in the case of K1 local K theory.
Okay, I have a question.
Uh-huh.
So isn't this the perfectoidization of spec R?
So it's not quite the, right, so it's not quite the perfectoidization. If you're over a base perfectoid ring, it's the derived saturation of the perfectoidization, but also
The derived saturation.
Right, so yeah, so maybe, yeah.
So this is what a W does. The saturation thing is what a W.
No, W is a bit vectors.
Oh.
Yeah.
I know, but like, wait. So if you're over a perfectoid base, isn't the R gamma R P literally the perfectoidization?
So when Yeah, so that's if you do the p-complete arc topology. Maybe
And isn't
let me,
arc P the p-complete arc topology, or is not?
no, arc p is where your valuation ring where p is not 0.
Okay.
Yeah. So maybe let me. I'll try to answer that in a little bit more detail.
Thanks.
When I get to that. Yeah. Thank you. Yeah. All right. So yeah. So this is somehow something which I think would be interesting to understand better. So maybe a question is, can one actually compute in sort of in geometric examples, compute the right-hand side, and in particular to connect with the computations of Hausel-Holt and Knudsen. So somehow this is a purely arithmetic question of computing some cohomology groups that may be interesting. Okay, so I have about 15 minutes. So so maybe let me start by trying to explain a little bit of what goes into the proofs and what was sort of the new ingredients here. But maybe I should pause if there are any other questions about the statements at this point. And I will try to explain what the statement of theorem C means when I get to it, the last part of that. Okay. So maybe let me continue. Right. So now let me say something about the proof of the first result. So let me say something about the proof of the H-descent property of K1 local TR. Right. So the main ingredient that this result uses is a following definition in Theorem due to recently due to Land and Tama. So they use the following very nice definition. So let E be a localizing invariant. So let E be a localizing invariant on, so I'm only going to use it, say, for Z linear categories, Z linear stable infinity categories. Right, so a localizing invariant is something that you can evaluate on a stable infinity category such that if you have a Verdier quotient sequence, it goes to a cofiber sequence spectra. So it sort of axiomatizes the features of algebraic K theory, which is sort of the basic example of a localizing invariant. And TR is another example of a localizing invariant, can be defined as generality. E is said to be truncating if for any connective HZ algebra, so when I have a connective HC algebra R, then the value of E on R is the same as the value of E on pi 0 of R, which is just a discrete ring. So they call such invariants truncating, and they prove the following theorem. So the theorem is that if E is a truncating invariant, then when you apply it to schemes, it satisfies CDH descent. And it also satisfies excision on the category of rings. So the CDH descent part is proved using using techniques or can be proved using techniques with derived blowups that were introduced in the work of Kurt Truncating. Okay, so right, so you get the CDH descent property, so in fact the right. So somehow the result that started this project was the following theorem, which is that K1 local TR is a truncating invariant. Let's say on Z linear categories. So in particular, you get the CDH descent and excision by these results. And let me mention that this was proved previously for K1 local TC. So TC is the Frobenius fixed points of TR. And this result was proved previously for K1 local TC by Land, Meyer, and Tama. Well, in an equivalent form, in work with Bott and Clausen. So K1 local TC has this truncating property, and somehow the starting point was that, in fact, it's true for K1 local TR. And so, in fact, well, so maybe I don't have time to say much about the proof, but the proof is completely different for the result for K1 local TC. So actually, there are two different proofs. Well, the proof by Landmeyer-Tama and the proof with Bott and Clausen are completely different proofs. But the proof that K1 local TR is a truncating invariant is somehow, well, I think maybe I should just say that the idea is that if you're going to see non-trivial K1, so K1 localization is a periodic localization, and TR, is built starting with THH. So THH of a ring is an Eilenberg-MacLean spectrum, and TR is a periodic or K1 localization is a periodic localization. And so somehow what's happening here is that you're trying to estimate the orders of nilpotence of the Bott element as you go up the TRN tower, and estimating them in an appropriate fashion, well, leads to this theorem. Okay, but yeah, somehow it's a purely topological argument, and so that gives you CDH descent. And now the observation is that K1 local TR also satisfies finite flat descent. And in fact, any K1 local localizing invariant has this property by a result of Clausen, myself, Nelman, and Noel. So you also get finite flat descent for free. And now it's a general fact that CDH descent plus finite flat descent implies H descent. So I believe this fact is due to Bott and Schulze. And so from there you get H descent, essentially from some general topological reasons. And this H descent result is somehow, it does give you some concrete statements. So as I said, this is, as I said earlier in the talk, there's a notion of a sheaf of spectra. This is well, the notion, the non-hypercomplete notion of a sheaf of spectra. Sometimes it's a little bit hard to work with because you can't test things by looking at stocks. But on the other hand, you do get some concrete statements about it. For example, the statement here when you have a finite group action, which is sort of Galois after inverting P. Okay, so maybe I don't have time to say too much about the proof of theorem B. So let me try to say a little bit about the proof of theorem C, and let me try to define the objects in the statement of theorem C. Right. So this uses the notion of I guess it's formulated using the arc P topology. And so there's the following definition. So I guess this was made in work with Bott, which is that there's a topology on the category of commutative rings such that, well, I should say really the opposite category, but okay. Such that A to B is an arc P cover if if somehow you can lift along valuation rings. So if for every rank 1 valuation ring, every rank 1 valuation ring every rank 1 valuation ring V, where P is not equal to 0 and is topologically nilpotent. So P is so in other words, the maximal ideal of V is the radical of the ideal generated by P. And whenever I have a map from A to V, well, I'm supposed to be able to extend that over B, up to extending the valuation ring. So whenever I have a map like this, then there is an extension of valuation rings, and I can assume that this is a rank 1, that W is also a rank 1 valuation ring, and a commutative square. So mapping to B, and then A mapping to V via F, and so I can fill in this commutative square. Yeah. So this defines a topology defined in terms of these valuation rings, called the arc-P topology, right, so that's defining what was the statement of theorem C, which is that you take the cohomology of the Witt vectors on the structure pre-sheaf with respect to this topology, also all of its Tate twists. And maybe let me just say very briefly what goes into the proof. So in fact, let me say a little bit of where the filtration comes from. And well, for that, in fact, I'm not actually going to need anything about this arc-P topology, so feel free to ignore this. So proof of theorem C, let me just try to say very roughly what's going on here, and in a sort of direct fashion. And let me just state it in the case you have a DVR. So suppose K is a p-adic field, so suppose what this is saying is that we can, the goal is to describe the K1 local TR of OK and to construct this filtration in terms of some objects which I sketched definition of. And here's the idea. Well, consider the algebraic closure of K. So consider K bar and its ring of integers. And its ring of integers OK bar. And so then we have a comparison map. We have a comparison map from the K1 local TR of OK to the, well, I'm first going to take the K1 local TR of OK bar, and now I'm going to take homotopy fixed points for the Galois group of K. And I take these in some continuous, sense of the homotopy fixed points. So somehow the claim is, well, first of all, that this comparison map is an equivalence. So this is sort of like the H descent that I explained earlier, except in fact it requires a fair bit of additional work because you're now not working with a finite extension, but an infinite extension. And this is actually where it's very helpful to use this theory of topological Cartier modules. I mean, essentially the issue is that TR does not preserve filtered colimits. So actually it somehow takes a little bit of work to deduce this from a finite type statement. And the next claim is that K1 local TR of OK bar is accessible. And in fact, this was essentially done by Hesse-Holt. So this is, I guess this is due to Hesse-Holt. Yeah, it is done but in this case, it is due to Hesse-Holt. More generally, the reason is that OK bar, its P completion is perfectoid. And for a perfectoid ring, you can compute the TR in its K1 localization. This was done by Hesse-Holt in this particular case, and in fact, it generalizes. So this is accessible, and it's in fact it's almost given, well, almost in the technical sense, given by the vid vectors of OK bar. And then you put those two things together, and that gives you the filtration. Okay, so I think this is a good place to stop. So thanks a lot for your attention.
Yay, thank you so much. Didn't you hide the appearance of arc descent here?
Right. Sorry. So maybe yeah. So I guess what happens. Sorry. So maybe the main thing that what I should say is that in general, when you want to describe, so in general, what this theorem C. So right. So let me pull up theorem C. Theorem C is based on you make some sort of Galois extension to a perfectoid, prove that you have Galois descent. So this is an infinite Galois extension. So there's some, so you have to make some additional argument. But then for perfectoids, when you form the K1 local TR, you actually do get this arc P cohomology coming up. And actually the reason it is somehow it's just that, well, if you have a perfectoid ring, well, perfect FP algebras are an example of perfectoid rings. And perfect FP algebras have trivial K1 local TR. So essentially what the arc P topology is doing here is that you already this statement is, this filtration is something that is true for any perfectoid ring. And what it's doing is essentially it's throwing away anything that's coming from a perfect FP algebra equal characteristic. So yeah, sorry. So maybe I should have explained that a little bit more clearly in the talk. But yeah, essentially this filtration. Well, if you think about the Thomason filtration as coming from étale descent or pro-étale descent, this filtration is coming from a sort of pro-étale descent in the generic fiber in this fashion when you start with OK and go all the way up to OK bar and form the Galois descent for that that extension.
Mm-hmm.
So is this filtration the Postnikov filtration for the arc P topology?
Yes. This is, so you can define this filtration completely invariantly as it's the Postnikov filtration in the arc P topology on all rings. But then the issue is that it's not clear exactly when it's going to converge. And so somehow then the conclusion or the theorem is that it does converge on this class of rings. And I don't know exactly what the best class of rings for which it converges would be.
But the associated graded is the same for any ring, right?
Right. So the associated graded is sorry. So the associated graded is exactly this object, this arc P cohomology, right. So but in general, there's no reason for the filtration to converge. Yeah. So maybe I can just also say briefly that this arc P cohomology, I guess this result is sort of strongly suggesting that if you're in the setting considered by Hesselholt and Madsen, so if you have something formally smooth over OK, then this arc P cohomology should be recovering their absolute Durand-Witt complex, maybe with mod P coefficients. And this seems like it would be a nice computation to, well, I don't know how to get started with this computation, but it seems like it would be nice to be able to somehow connect the two approaches. Sort of this approach to, yeah.
If instead of a ring R, you wanted to put in a kind of scheme, do you have any comments on that?
Well, I guess, right, so I guess so TR is I guess I stated everything for rings, but if you, so TR is a localizing invariant, so it will satisfy Nisnevich descent, so it will work well for QCQS schemes. Yeah, thank you for the question. Yeah, sorry, I guess it's a little bit easier to, this arc P topology, somehow it's easier to formulate that when you just work with the rings. But, yeah.
Sorry,
but actually when you, yeah, sorry.
What were you saying?
Oh, I was just going to say, right. Anyway, I guess sort of implicitly, like when you talk about CDH descent and so forth, that's proved by doing some blow-up constructions. So you do leave the world of affine schemes. But yeah.
Sorry for a naive question. So in the definition of localizing invariant, there is nothing about descent. So you're saying Nisnevich descent is a, so it follows, as like in Thomason's proof, you can repeat it. Oh yeah, okay, good.
Yeah, so Thomason, right, so the theorem is that any localizing invariant, when you apply it to schemes, it automatically satisfies Nisnevich descent. It's in other words, it's a Nisnevich sheaf of spectra in the non-hypercomplete sense in general, and if you have finite Kroll dimension in the hypercomplete sense. Yeah, so that's sort of a very general descent result that you have, and sort of if you add the hypothesis that your localizing invariant is truncating, then you get CDH descent. You get something much stronger, and if you add that it's K1 local, you would also get H descent. So yeah, so thanks for the question.
I have a dumb question. Is there a reason to think that K1 localization of these of K theory and TR should be amenable to such results as opposed to KN localization or EN localization for Johnson-Wilson theory?
Well, I guess
for higher heights.
Well, I guess in this context, I'm only considering I'm only working with ordinary rings or Z algebras, but it's truncating, so you may as well work with ordinary rings. And for those, there's no higher chromatic information by Mitchell's theorem.
Right.
So this is sort of the only thing that you can consider.
So there's also E1 localization.
Yeah, but right. But I guess
that's stupid, I guess, or.
Well, I guess I'm only considering everything in the P complete context. So I think TR is naturally a P complete object. So
yeah, thanks.
Yeah, so I'm not sure.
Well, I said it was a stupid question. So
well, you can define TR. Right. I mean, I guess you can define a non-P complete but P typical version of TR. So you could ask the question for those. Yeah, but I'm not very sure. I mean, yeah.
Doesn't this boils down to understanding K1 local TR for every prime and rational TR, whatever rational TR is? Understanding E1 local TR, right? By the square.
I guess so. Right. I mean, I guess I was already sort of working with P complete rings, so TR will not have any information away from P, but you could try to get some rational information. All right. Yeah, I haven't really thought about it though, so I'm not completely sure.
Are there more questions?
I'll ask another stupid question. What about moving away from discrete rings and looking at simplicial commutative rings?
Right. So I guess it's a truncating invariant. So K1 local TR will only depend on pi 0.
But I guess then one could ask questions about like K2 local TR.
Right. So definitely one could ask. One could, for example, input a ring spectrum with sort of higher chromatic information, and then ask about like the K2 local TR of it, and I agree that would be interesting. I don't think I know much about that question. In fact, I think a lot of the methods I was using were sort of specific. I'm not sure that they, like for example, this fact that they're truncating, I think is, yeah. So
powerful.
I'm not sure if there are, but it certainly would be very nice if there were such analogs. I agree.
Thanks.
Yeah, thanks.
Okay, if there is no more questions, let's thank Akhil again. Maybe you have more questions.
Thank you.